Thanks, Simon. Well, there's no shame being number 2 to guys talking about pythons and bars. I mean, it's like the perfect combination. You can't compete with that kind of talk. I'm glad he's not here this year, or is he? Yeah? Oh, no, fail! There goes my plan for world domination. Anyway, right. My slides up. Okay, perfect. Right. So, thanks for the introduction, Simon. So, another Simon, in a long line of Simons in Python. My name is Simon Ratcliffe. I sort of wear a number of hats. I put up the hat slide just as an excuse if the talk kind of lulls and I've lost my mind because I've been doing too many other things of late. So for Meerkat, I'm the technical lead of scientific computing, which is all very grandiose and doesn't mean anything really. The SKA project, which I'll talk a little bit about, is this really big, mega telescope, and for that I have the dubious honor of being the system engineer for the science data processor, which is mostly pushing papers around. There's also the DOME collaboration, which is a research sort of topic into exascale computing being run in Europe with Astron and IBM, and a whole lot of other bits and pieces. But anyway, that's not important. What is important is to prepare. So, prep, launch, right. Let's begin and see. Just give a reasonable size cluster. Okay. Let's just make sure that's going to work. You never know. It seems okay. So, of course, we have these grand ideas, these beautiful demos. And you only discover the night before that the default AWS account only limits you to 20 instances. I was like, I'm going to do 1,000 instances, 1,000 nodes. People will be falling from the trees when they see my demo. Then I'm like, go launch 20 nodes limit. And then you can mail AWS, but it takes 3 business days for them to respond. So, maybe they'll respond immediately, like in the next hour or so, and then we can do the demo. Anyway, that's happening in the background. So enough of that. On to astronomy, which is, of course, not Python, but that's what I'm talking about today. In the beginning, long time ago, there was bang and all sorts of stuff happened, and we're right at the very end there, that little tiny like pixel sliver on the right-hand side there. That's us. That's the whole history of human development. Basically, where we are now, cold fusion, jetpacks, flying cars. Well, it's probably a rounding error, so a little bit back from that, but we're still like a pretty cool time. But it wasn't always thus. As humans, we've had some hazards to deal with. I particularly like the picture of the guy with like grapes growing out of him and like volcanoes and snakes, and that was like properly trying to get to work in the early days. You had to deal with these hazards. But as time went on, the volcanoes settled, the snakes disappeared, we killed off the saber-tooth, Sharktopus got bad ratings and went back to the netherworld. So we started to overcome these impediments in our sort of getting in the way of doing interesting things. And so with our free time, we started to look upwards and look at the heavens and think, what is this all about? All these beautiful stars flitting around us, what does it mean? And it was really the Babylonians who kicked off the whole thing of astronomy and actually doing useful things with looking at the sky. This particular example is kind of known as astromagic, which is actually a cool field. I'd like to study astromagic. It sounds fun. Essentially, whoever did this could sort of do some predictions and then use that to go to the landowners and say, I can tell you when the clouds are going to come, when the rain is going to come, etc., based on my studies of the heavens. And that sort of helped us on for a long time, and this basic visual observation of the universe helped us understand a lot about what was going on. But we needed a kind of a next step forward, and that's because if you look up the night sky, and even if you go to a really remote place, so this is a picture of our site in the Karoo. Obviously, it doesn't actually look like that, but we've got a nice stellarium plug-in which makes it look cool. You can go there, and even on the best night, you can only really see about 20,000 stars. Now, given that our galaxy has 100 billion, a 20,000 star survey is a pretty small drop in the ocean. So what we need is to develop something better. And so along comes Galileo, commonly known as the guy who developed the telescope. Actually, what he did is he bumped into a guy called Hans Lippertje, who was a Dutch optician, saw the telescope and said, I can sell this, and then I'll give you some of the profits. So he went back to Venice, he patented the idea, he sold it to the court there, got a huge increase and lifetime tenure, etc., and poor old Lippertje died in poverty, probably. Basically, Galileo took someone else's idea, made it wildly popular, made a lot of money, so he's pretty much the first Steve Jobs. Sorry, people. Moving on from such controversy, things progressed. People built bigger and bigger telescopes. I always talk about Johannes Sibelius. Those people who were here last year will remember me banging on about him. But what I like about him is he just built these insanely big things. He built them so big that they just fell down and broke. But I think that sort of secretly pleased him that there's such destruction going on. So we get to kind of today, where we stand. This is a picture of SALT, the Southern African Large Telescope in the Sutherland. And we can see an appreciable fraction of the universe with optical telescopes. And we can see amazing things. We can see, a picture there of Centaurus A. That's a whole galaxy, hundreds of billions of stars there. And the fact that we can kind of routinely see this is pretty amazing. But the thing with optical astronomy is it's only a little tiny piece of the puzzle. If you look at the visible light bit in the electromagnetic spectrum, we really are not seeing a lot of what's out there. So we need to go further. And that's where radio astronomy comes in, and other types of multi-wavelength astronomy. But what's particularly interesting about radio astronomy is, if you look at the picture in the bottom right there, you'll see if we didn't look at this thing with a radio telescope, we would just see the galaxy there. We wouldn't see these massive jets of gas the same size as the galaxy itself coming out. And so that kind of gives you a little hint at why we need to do these kind of multi-wavelength observations. There's a downside, though, with radio astronomy. And the clue with radio astronomy is to look at our units. So our unit of flux is a Jansky, which has a 10 to the minus 26 watts in it, which is pretty appalling. The picture below is just some typical sources that we look at. Those are actually millijanskys, so it's like 10 to the minus 29 watts. So that's a big problem. The other big problem are the baddies, of course. We look at these sources that are very weak in the sky, but we have things that are interfering with us. The sun, 10 to the 5 Janskys, so 8 orders of magnitude above what we're looking at. Someone standing with a cell phone at 1 kilometer away, 10 to the 8 Janskys. If you have an iPhone, it's fine because the battery's flat anyway if you're using iOS 7, so no problem there, it doesn't hurt us at all. So what do? Then we need to think about scaling up and scaling out. That's to build our telescope. So in the 30s, we had these kind of quite small, tiny dishes. Things got bigger and bigger. We moved them away from civilization to avoid the baddies that were interfering with our observations. And this is what we built in the Karoo. So this is the idea of scaling out your telescope. Instead of building one big, massive one, which if you build it too big, falls over. And I've showed the fall over picture so many times, I thought, well, I can't tell the same joke at like every Python conference I ever go to. So it's time for some fresh jokes. When you hear a fresh joke, please let me know. I don't know if I actually have one today. So this is sort of one we made earlier, sitting up in the Karoo there, 7 antennas. And that's kind of what we call a pretty small telescope, but it's just a precursor to building bigger and bigger things. So we have a telescope under construction now called Meerkat. Very cunningly named More of the Same, More of the Cat telescope, which we've already built. And that'll be 64 of these antennas. To give you a bit of a scale perspective, these antennas stand sort of 15, 16 meters high, with their pedestal included, so they're pretty large structures. And we've just started breaking ground on the next sort of tranche of these 64, and we should finish them like 2015 timescale, something like that. That's kind of what it looks like on the ground at the moment. There's a whole lot of construction work going on, building roads, building runways, et cetera, et cetera. There's a really nice gigapad if you want to go and have a look, and you can see kind of what's happening there. We should have webcams becoming live on the site quite soon, and you'll be able to sort of follow the construction. It's quite amazing how, if you have a couple of 100 million lying around, what you can do in terms of bulldozers and moving Earth around and changing the face of the landscape. It's very nice. But this is part of a path that we're following to what we call the big telescope. So, we've started with 7 and then 64, and our end goal is known as the SKA, the Square Kilometre Array, and that's a telescope that, when it's finished, will have 2,000 to 3,000 of these antennas. So, you can imagine just driving up there to the Karoo, and you kind of go over a hill, and suddenly there's this sea of antennas just lurking out there in the middle of nowhere. It's pretty impressive. And so that's our kind of end goal, big telescope. But, to make big telescope happen, we need, well, we don't need, but we get lots of big data. So again, this is a bit of a recycled joke, but it's such a pretty slide, I'd just like to leave it in. It's got lots of numbers on it, and that's cool. Anyway, it tells you that we can have a lot of data. So particularly in this case, the SKA, we're talking about roughly an exabyte of data a day that we have to do something useful with. I mean, the raw data rates are a little bit higher, but a lot of that we can discard. So I was thinking about, exabytes are all very well and good. This is what really brings it home for me. If we look at the difference between an XB byte and an exabyte, so if I go to my vendor and I say, vendor man, please sell me an exabyte, the difference between what I really wanted, which was an XB byte, is 38,000 4 terabyte drives. That's what gets lost just in our IEC unit catastrophes. And it's a rather large amount of data we're going to have to do something useful with. Of course, Python's the solution, so no worries there. I'll get to that. in addition to big data, every challenge is big. So, you know, I can just start off with every slide with big something, big this, blah, blah, blah. But big energy is quite an interesting one. When you start building facilities at this scale, things that you wouldn't really have thought about as an issue start to come into play. And energy consumption is certainly one of those. So we did a little study to look and see what is the energy cost just of moving the data from these antennas back to a central location. Because basically what you do is you have to record the signal at every location, bring it back to one point, and you cross-multiply them all together. But some of these telescopes will be sitting on maybe 2,000 kilometers away. And overall, the energy cost of just bringing that data back to one place, somewhere in the region of 16 megawatts. So you're kind of building a power station just to move your data to your sort of central processor, let alone powering that and everything else that you need to do. So, you know, it's nice challenges to have, I guess. So someone's got to figure this stuff out. So how do we build such a thing? I apologize for maybe I'm too strident. So what we need to build is big iron, of course. This is personally what I think we should spend our money on. You know, software and hardware and computers and so on. But I mean, if you have one of these things, I mean, just, you know, it's like imagine hanging out the cab of that bad boy. Like, this is what I do. I drive this thing all day. So much better than writing software. We're definitely in the wrong profession. The kind of big iron, of course, we need is this. Lots of flops, lots of, you know, many, many gigabytes and terabytes of data moving around, et cetera, et cetera. So SKA, the final SKA, we are talking in the region of a couple of exaflops worth of processing, which has to sit out in the desert. It has to work reliably, et cetera, et cetera, et cetera. It's not going to be mollycoddled. So there's some challenges to get to, you know, to make it work and work well. If you go to the vendors, this is what they'll sell you: big, serious computers. You go to IBM and they'll say, "Ha, I have this for you. It's a proper computer. It's blue and flashy and nice." And the problem with these kind of traditional computers, to some extent, what I call a traditional computer, is for our problem, particularly for astronomy, they're quite misfocused. For us, flops are not really the issue. It's getting a decent Amdahl ratio, which is having a good number of bits of I/O for each of your flops. Is to try and balance the load of I/O coming into your machine and the number of flops. So one of the things we can do is we can start to look at, say, well, where's the industry driving this stuff? So certainly, in my opinion, the rise of the SoC, you know, everyone's carrying around these supercomputers these days effectively. What's particularly interesting about the SoCs is that you have a relatively small number of flops and a relatively large number of I/Os. I mean, there's a part from Freescale we're using that's got 4 40-gig interfaces and only about 100 gigaflops of processing power. So that's a really interesting kind of computing part. And one of the things we're investigating is taking a whole bunch of those and throwing them in a box, essentially. You can take a couple of thousand of these because they're so low power. You put them in a nice oil... is that me? Someone else? Sorry. You throw those into an oil bath, and then you kind of seal it up and weld it shut, and then drop it out of plane and leave it in the desert to sort of suffer along in silence. But because it's so low power, it's very easy to build infrastructure around these things to make it work. Oops. We also need big storage, obviously. So Meerkat, we've got we'll have like 10 petabytes or so, which is pretty straightforward and easy enough to handle. The SKA will need an exabyte of storage. I put the old tape there because tape is wonderful. It's the way of the future. I tell all the youngsters you should get into tape. Tape is the way. And tape is beautiful because it's no watts. You throw your data on it, then you leave it in the cupboard for 10 years, and then you get it again, and it's possibly still working. But compared to your spinning discs, you should try as a good experiment. Take your disk, shut it down, leave it for 10 years, start it up again, and then let me know the results. But the results are that it will fail. They don't like being left around doing nothing, those discs. However, I was trawling eBay the other day, and exabyte for $20. It was sold, but I'm hopeful that there'll be another one along shortly. So, we probably don't need to worry too much about the exabyte. Right, imager, stage 2. So, now, has my cluster started? Oh, genade. The thing is still running. That's fine, no problem. I shall waffle on regardless. Let's go back and talk. Remind me to come back to that shortly. So, big software. Okay, so now you guys are all fallen asleep with hardware and crapping on about astronomy. Software time, we can talk a little bit about that. Obviously, if we're going to build big software, we should choose the language, the lingua franca of big software, which is obviously COBOL. 200 billion lines of COBOL, can't be wrong. I don't know what we're doing with Python because clearly the tide is against us. Punch cards, fantastic. So this is the software problem we need to solve, basically. It's nice to put an equation in a box full of magic. So the magic is what we're trying to figure out at the moment. Essentially, what we need to do is our telescope measures the ideal sky in a very corrupted way. If we had lots and lots of money and lots of time, we could build a really big facility that basically tiled the ground with receptors. So instead of having a dish here and a dish over there and a dish over there yonder, you would just build massive dishes everywhere, and you'd capture all the signals that you were interested in, and you wouldn't have, you'd have fewer problems. Because we build this kind of sparse array, we're effectively subsampling our problem, and that introduces quite a lot of issues. So our task essentially is to unwind all these effects that we have, and there's a multitude of effects. Everything, you breathe on the telescope wrong, there's some new effect you have to take into account. But essentially, that's why all our I/O and flops and kilowatts and dollars go into fixing this equation, so that the things we measure can be equated back to the ideal case. And that's primarily in radio telescopes these days. Primarily is a software challenge. So I'll always put David's quote here because it's just the best quote we've ever heard. It's how it is. My quote would probably be, "I'm too stupid to write C++," but it sounds better to say life is too short to write C++. Certainly templated C++ is not for me. So this is our kind of philosophy that we have to combat the malaise of big software, because as soon as you start saying to someone, "I'm going to write big software," then again those serious people in the lab coats come out and they say, you need 50,000 million people to write this software because it's going to cost so much money and this, that, and the other thing. So we sort of try to stick to some of these principles. I think optimizing last is probably my favorite amongst all of those. I think what optimizing last tells you is that there's too much assumption about my problem is going to be intractable and it's going to be too difficult, and I must immediately start writing in assembler, because it just can't be solved. I need to, I've got to do a regular expression on this long string. It's going to be too slow. So the idea with optimize last is to say, well, put your good ideas in place, prototype them quickly. It's very agile and rapid, and this is nothing new, but it does go to language choice quite a bit for me, in that choosing a high-level language up front is saying, okay, I'm going to optimize later. I'm not going to optimize up front. I'm not going to assume the problem is too difficult to do. Let me actually have some real numbers that prove my problem is too difficult with my current tool set, and go on from there. I'm going to quickly see what the state is. Woohoo! Cluster is up and running. So let me do that. And apologies for the copy and paste. I know this is all very non-slicky. Right. That's my local one. Let's see. Everyone hold thumbs. Whoops. Let's try that again. Whoops. Wait, no. Aha. Keys. Always forget about the city key. There we go. Sweet. And nervous tension. Too much. Look at that. Spectacular. Okay, so what I'm going to do is I'm just going to start this reduction, and then I'll come back at the end and talk a little bit about what it's all about. Essentially, what we're trying to demonstrate here is kind of live, real-time reduction of real Cat7 data into a useful image using AWS and specifically the notebook, because the notebook is just awesome. Let's run all that. Okay, back to the talk. So we'll see what happens in the background. So, I mean, this is preaching to the choir, of course, but I put these slides in here because, particularly in radio astronomy, whenever we tell a radio astronomer person that we're going to use Python, they're like, rah, 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 rah. So I put these slides together to sort of, anti-rah, rah, rah them. But, Python's obviously, it's slow. No, it's really, really, really terribly slow. Mostly it's, it's a signal and antenna type issue. I should put an Android phone there, I guess, to be an equal opportunity something or other. But anyway, it works for now. Obviously, it's just a matter of how you use the tools you have at your hand. If you use the thing in the wrong way, it's just not going to work well. And it's just thinking about your problem in the right kind of way and using the right kind of tools. So I always put this up here as a kind of a teaser for the guys, because I know what's coming next, and so I have a slide I don't even need to talk. It's like, yes, I know it's C, but I didn't have to write any C, which is fantastic. And yes, my KLOC count is down compared to all the other people who write reams of code, but that's okay. I don't get paid by the KLOC. I don't know what the metric is, but there's some other metric that we can use. Obviously, we're still a little bit slower than C, but again, this comes to this kind of like optimize last, optimize first type debate. And for me, it's not really particularly about the language, that it's how you use it and what you're trying to get. So you've got to ask yourself all the time, how fast do we actually need to be? And in our domain, that's our CPU, the future prime minister. He has his way. And it's mostly sitting there doing bugger all, just waiting for some data, yawning, laughing at us. 8 cores in your cell phone is really, this is it. It's just ridiculous. What the heck's going on? So a particular radio astronomy problem is gridding. So our data we collect on an irregular grid, and we want to FFT it so that we can, we want to regularize the grid so we can FFT it. DFT is going to be too expensive. And so we spend a lot of compute cycles on regridding our data. In that process of regridding, we make use of the convolution kernel to do some fixing of some of the effects we were talking about earlier. Essentially, the bottom line is that the gridding is a pretty simple process. So if we look at a relatively modern CPU, obviously a 2690 is pretty old these days, but we need around 64 gigabits a second to keep this core busy, and that's quite changing. That's actually supposed to be gigabytes a second. So I was falling asleep last night. That's ridiculous. Big B there, read it, everyone. So you need lots and lots of data to keep the CPU maximally fed. And in reality, we probably have an order of magnitude there. So there's the outrageous claim of the day. If our hour is efficient, we can sacrifice an order of magnitude in performance in the CPU. Essentially, what I'm saying there is that as long as we are making the bits that are bottlenecking us efficient, the rest of the time we can afford to save money effectively on developer time and spend it elsewhere that will give you better bang for your buck. So is our IO efficient? Yes, I assert boldly. I had a whole 10-slide debate on proving, well, not debate, but a whole 10-slide diatribe on proving our IO is efficient, but basically just trust me. The IO we're doing with Python is pretty efficient, and there's quite a lot of tricks you can do to make it so. But I think fundamentally, and people, other people who know a lot more about this will talk about this further today. I think there's a talk on bitcode. It's not really about the language. A lot of it looks pretty similar underneath. It's about getting to efficient bitcode, and it's having an expressive and high enough level language that you can quickly get to decent bitcode. And I think as we move into the future, if you look at the success of LLVM, we're really getting to the stage where we're going to be language pretty agnostic. You're going to write your language in whatever, write your top level code in whatever you want, and then you'll compile it, and you'll let LLVM take care of running it on your GPU or your many core Xeon Phi, whatever the story is. I think we're kind of moving on from this whole like you've got to have your language is so specific to the task you're trying to solve. And I think that's pretty exciting for us, and I think it offers up good advantages. So as I said, for us, in many ways, our biggest cost is development time, not hardware. Especially if you look at it over a good span of years. Our Dutch colleagues have just done an experiment where they were forced to do it because their Blue Gene that they were using ran out of warranty and licenses, and then it just explodes, I think, when the license expires or something. Anyway, they had to stop using it, so they built a GPU-based solution, and 2/3 of their budget went on development and only 1/3 on hardware. And that's because they were writing the stuff mostly in OpenCL, which is, as those who've used it, it's a pretty challenging language to write a lot of big software in. So, onto ourselves in SKA South Africa. So, we're quite a heavy Python shop, so I show the usual cloud of logos that we use. We're a fairly equal opportunity. We use sort of pretty much everything and anything that's going. And we use Python pretty extensively, through our telescope. Indeed, our hovercraft is full of eels, from the control system down. So we really try to push Python into many areas that people would say are non-traditional in this kind of environment. So we don't just have it as a kind of scripting glue framework. We have a lot of our code and more all the time that we're rewriting in Python. We're taking old astronomy code and finding that because especially this legacy code is so complicated and has such a long, tortured history, that even though the individual, on a line-by-line basis, that code is pretty fast, taken as a whole, as a big software package, it's actually pretty slow. and you can find that you can actually you can be very competitive rewriting that stuff in Python, just because the expressiveness and the syntax that you're able to use lets you write that much simpler code, and it's much easier to debug as well. So our control system, we've been using IPython for a long time, since kind of day dot. We showed a demo of this last year at PyCon, where we connected live to the telescope and you controlled it. What's quite nice is it's kind of an introspective-based system, so there's no static configuration about what's out there. Rather, you connect to devices and you figure out in sort of real time and on the fly what's available to be used. And that's worked very well in terms of an emerging and developing telescope. Even things like our data transport, we have obviously C implementations of this, we have an FPGA version, but fundamentally it looks like we're moving NumPy arrays around. We use the NumPy header syntax in our data transport. And it's really nice because sorry, I'm just going to drink water. It lets you glue everything together very efficiently, a whole range of disparate architectures. All right. Time to see what's happening. So, let us go. Let's see, okay, it doesn't say kernel busy anymore, which is good. And, aha, there we go. Okay, so let me tell you what happened here. That was what was supposed to happen. Yay! Okay, so, okay, I'm just loading up this other notebook. So, how many are using the notebook actively around here? Just a couple. I mean, it's probably more relevant to the kind of stuff that we do, but I would encourage people to use the notebook. It's just a fantastic tool for sharing and developing, and if you use IPython at all, you really should be using the notebook. It just adds a whole lot of extra niceness to things. So one of the things that we're trying to do, and I'm particularly interested in, is reproducible science. And excuse me, this is something that in our regime hasn't really been sort of thought about well enough in the past. People will publish a paper with some scientific results in it, and if you want to reproduce those results, either as an independent person or even if you want to reproduce your own science, it's often a major challenge. You've got to go back and think, what version of software did I use? What were my configuration files like? What script did I use? Where's that data? Does it even exist anymore, the data I used? And so I think the notebook is a great tool for exploring that idea of open and reproducible science. And what I've tried to do here with this demo, and I'll step you through what we've done, is basically written up a Cat7 data reduction in a notebook. And there's a fair bit of serial stuff in here that still happens. We're in the process of parallelizing everything as we go. But basically, it takes a real raw data set from Cat7, performs a whole lot of calibration steps on it, and then does a parallel imaging run, and we parallelize it across frequency, and produces the thing that produces is the final product that we would give to scientists. And the idea with this, and what's hopefully cool, is that all you need is things like, what AMI did I use? I mean, this is Amazon specific, it could be anything, obviously. If you know the AMI that you used and the EBS volume that your data was on, and the idea is the notebook would be in GitHub, then you can go and you can check out what someone else did. You can check out their scientific paper effectively, and you can rerun it at your own leisure. You can change parameters, you can tweak things, you can see intermediate results, etc., etc. And the idea will be that every product we produce out of Meerkat, and possibly the SKA, all the science that we produce won't just come with a single image. It'll come with this full infrastructure around it. So the full notebook showing exactly what went into making this product. And hopefully that introduces a much more sort of open environment to the science we're doing. And so it allows me to come back and say, oh, I made a mistake, I can tweak a parameter, rerun it, and off I go. It also allows, as I said, independent people to come and have a look. So I'll just go through a little bit. There's a lot of initial setup here. Laugh at my code, please, because it was all written in a rather much of a hurry. So the first thing we do is we look for a bunch of calibrator sources. So these are things that are known in the sky. So when you do an observation and you get some data, what you need to do is you need to bootstrap that data. So you need to know, okay, that particular thing that I can see, that's well known. People know all about it. They know how strong it is. They know its characteristics. And they can use that and apply it to the rest of the data to make sure that everything, all the sort of the measured power levels you get out make sense. I should put this bottle down before I throw it somewhere. Sorry. So then there's an ingest phase where we take our native data format. We use HDF5 at the moment to store our visibility data, and we do a whole bunch of things to it and effectively load it into this framework that we're using. Underneath here, there's a whole lot of horrible code, so don't look in too much detail. It's obviously not Python all the way down yet, but it's sort of getting that way. Then we do a whole sequence of excision and flagging. So as I mentioned, these nominal baddies out there that infect your observation and try to wreck the science you're trying to do. And so we go through our data and we have a look for these sources of interference. So we flag out, right, a GPS satellite has gone overhead. So we've seen that, we've taken it out of our data, and now we don't have to worry about it. Or, someone is using a cell phone, whatever the case might be, something that's gone wrong with our data. So we do that sequence of flagging, and that's kind of what we get when we look at our raw data. So that's looking at a few of the baselines. So baseline is what the signal you've recorded between any pair of antennas. So you can see here, this is antenna 6 with all the other antennas for the Cat7 array. This is a plot of frequency on the bottom and a relative power level over here, and the top plot here is phase. So this is showing you that across your band, so you record data across a certain frequency range, you can see it's very lumpy and ripply. You can also see that this phase plot up top here, this is, if you look at the scale here, 0 to 100 degrees is quite a movement in phase across the band. So that's stuff we need to take out and calibrate. So we do a delay calibration and we do a bandpass calibration. Bandpass calibration essentially says, right, there's a big source over there, and I know that it has a band shape that's flat, or I know it very well. I can then use that to take out this ripple in my data, which is just introduced by the telescope and not actually part of the problem. So you can see here now we've flattened this bandpass. It still has a slope because these sources have a spectral index. Basically, as you change frequency, the power received from that source changes. But it's much better behaved and well constrained when we go through these calibration phases. Then we do an amplitude and phase calibration. That tries to normalize all the levels that we have, and we correct all these so-called fluxes, all these powers. We compare them to the source that we're interested in, and basically then there's a pre-imaging step that goes. So what I ran here now was that parallel imaging. So I'm using the IPython parallel framework, which is very good. It's progressed a lot over the years, and we use it reasonably extensively, and we're using it more and more as we go. There's a whole lot of setup that happens. There's any number of parameters that go into our imaging. So this is kind of the area where when people come and they look at your observation, or there's something that hasn't worked out quite right, you can come here and you can change these parameters and then fairly trivially rerun things and get a different result. So there's a whole lot of parameters. I won't go into all the details of those. Use a little bit of scatter, send some seeds out to the various engines that I'm using. I look to see if my data is making sense. So this I just print out per node, the data I'm interested in looking at. As I said, this was our original glorious plan was for hundreds or thousands of nodes in parallel. So for those of you who've been paying attention will notice that I only used 15, which is kind of the Achilles heel of the allegedly glorious demo. But if it works for 15, it'll work for 1,000. Hey? I mean, simple scaling, no problems there. I promise you next year I'll have a fully fledged AWS account, and then I'll try to run it on 1,000 nodes, and we'll see how it happens. Then we do some further calibration. So this calibration gets done on the individual bands we're looking at. So what we've done now, as I say, we split it across frequency to give ourselves an axis of parallelization, and we're now looking at the individual bands as we go and calibrating those further. Then we set up the imaging task, and that's the sort of main meat and bones of the thing. It actually runs pretty fast. I mean, I'm only running this on T1 micronodes, which are pretty limited. But given that we've parallelized our data quite heavily, this was originally about a 10 gigabyte data set or so, and the imaging probably only took a couple of minutes to do in parallel, which is pretty good. And this basically then shows you what I do is you generate all these individual frames in parallel. And this is the image of the first and the last frames from that data set. They look pretty similar because we don't expect this field to change much with frequency. And then we take those individual frames and we average them and glue them together. And you can see that's what came up. I should have showed you beforehand that there were no results in this before I ran it, just to prove that it actually did run live and stuff actually happened. I can show you my EC2 management page. Let's see, there's some proof that things are actually real. Show me the proof, show me the proof. Maybe, maybe not, maybe that's a bad idea. Anyway, so now what we do is this notebook now can get saved up as it is. And one of the things that's really cool is, let's just open this, is you can take that notebook and you can turn it into a PDF, and you can basically take your reduction that you've done and you can write your, you can write your paper. You can include, math text stuff in here. Sorry?
We see a blue picture with spots. What are those spots?
I shall tell you about the spots. It's a good question. So you can basically take that notebook and make your paper straight off. This is just a simple NB convert. It makes a pretty good looking PDF that has all the explanation of what you did, as well as the code, as well as the results. So kind of everything's in one place. There's no like, my code is here, my results are here, my explanation is here. It's all kind of mingled in together. And I think this is going to be, for the future, I think it's going to be a pretty powerful, powerful tool. There we go. Some nodes are actually running and burning time. Yeah, I should have talked about this field a little bit further. So this is a field we observe quite regularly. We call it Deep 1, which gives it a sinister overtones. But essentially, it's just a fairly nearly blank patch of sky that we use to test out how deeply we can observe. So these sources here are kind of at the observing limit of what we can see with Cat7 in a reasonable length of time. This is about 10 hours of observation. These are just very distant compact radio sources, and they're kind of a couple of millijansky, so they're very small, and it's a nice testing field because some of them are quite close together. If I spent more time on this image and did it properly, you'd see that there are about 100 sources in there altogether. And again, there's a little explanation in the other notebook about the field, and there's something in here about the field and the observation. Here we go. Roughly 120 distinct radio sources. So these are galaxies with big black holes in them. So those, these are far away objects with, containing millions of stars themselves. Cool. Okay, so let's go back. I think. And right. So basically, that's what I had to show. Jacob Zuma says, "Come and visit the SKA." I give it the thumbs up. Here we are. But it's a really cool project, and I think what's nice about it is it's it's the South African government putting a lot of money into primary science, and it's in sort of 8 years I've been working for this project, we've come a heck of a long way, particularly internationally, where when we started doing this, you would go overseas and say, "I'm a radio astronomer from South Africa," and people would be like, "Oh, what are you doing? You don't even have electricity and email." And it's like, "But I just emailed you yesterday." People, "What are you talking about?" And now we go and people are like, "Yeah, radio astronomer from Africa, this is really cool." And we get to play with a lot of the big tech leaders and bring ideas back here and take ideas from here elsewhere. And I think it's really proved that South Africans, we have a strong community here. I was amazed last year at PyCon 2012 at how many people are sort of using Python and doing development in the Western Cape and in South Africa. It was really cool, and it's really good to see so many people here. I will use this as a little punt to put out like a call to action. We have positions. Everyone always seems to say that at the end of their talks, "We're hiring." So I thought I'd start off that process, and everyone else can follow that. So we are hiring. We're always looking for really like go-gettery, Python-y, tinkery, codery, hackery, build hardware, whatever you want to do. Kind of there's something we need to do. So come along. Drop me an email. You're welcome to visit our offices, see what we're doing. There's lots of cool opportunities for things, and yeah, I'm a little bit short, but thanks for the time, thanks for listening, and yeah. That's it. We're going to do questions.
And for one question or two, it's almost tea time. So if you have a question, raise up your hand really quickly. Okay, that hand right at the back, and this hand here in the second row. Shout if you want the mic.
I'll just repeat the question.
The person who put up their hand over here. Yes, you, I think.
Now known as hand one. Ah. The question was how far away are those galaxies that we saw in the picture there. I'm not exactly sure the exact distance. Tom, do you know? Halfway to the edge of the universe. So billions of light years away. So 5, 6, 7 billion light years distant, which is obviously pretty cool. So you got to see it happening live here today. Halfway to the edge of the universe and back.
So you guys obviously have a lot of data feeds coming from custom types of hardware.
Yeah.
Do you have any other opinion on Ethernet or any other standardized networking, or do you have sensor arrays doing DAC sort of things
Sure.
at any given point?
So as you say, our data flow involves a kind of number of hybrid kind of technologies. So we sample as early as we can. And so for Meerkat, our sampler is actually at the feed of the antenna. We digitize straight away. From there, it comes over 40 gig Ethernet. That's currently what we're using. The main reason for that is that our digitizer and our correlator are FPGA based. And gigabit Ethernet or 10 gig Ethernet cores are quite a lot simpler to make in VHDL than InfiniBand. So although InfiniBand would offer us some advantages, particularly the RDMA capabilities, we currently are Ethernet up until our correlator device. Post-correlator, where we get into kind of more commodity hardware, at the moment we've got a toss-up between Ethernet and InfiniBand for that.
Are you limited by backplanes there, or just optics?
So we're fortunate in that because we can parallelize our problem quite substantially, and we don't have a lot of crosstalk. For example, that imaging runner did, that's completely parallel. And so that does let us, we don't have to have a large kind of very high-speed mesh fabric. Most of it is quite this kind of simple router and then serial out along a couple of nodes. So yeah, we pretty much stream it out. I mean, we do need to look at the data in real time. So that's why we fall under the horrendous big data moniker, because we have data and we can't really store it for too long. But I think particularly with 100 gig InfiniBand basically here and working well, for the next 5-6 years, it looks pretty doable for us. I think when we see more accelerated technology that goes in socket as well, particularly with dedicated PCI Express links, that's going to be quite helpful for us. At the moment, if we use something like a GPU, obviously we waste a lot of time moving data across the PCI Express link.
One last thing on that you actually remind me of now. Have you guys fiddled with those 10 gig commoditized FPGA links that you can get?
We said
Do not have a need for it.
we've looked at them. We don't currently have a need. We use, at the moment, I mostly use Chelsea Onyx and some Mellanox stuff for the InfiniBand. And both of those have got pretty good access to the offload engine if you want to do something tricky there. But most of our data, it's all UDP, and we just basically zero copy it straight out, either into GPU memory or into sort of kernel space, and then do things with it there. We don't really need to do a lot on the NICs at the moment, yeah.
Cool. I'd like just to thank Simon again. This really is an incredible project, and it's awesome to see so much of it being done in Python and to see it happening right here in South Africa. If you have more questions for Simon, there is a tea break right now.
There we go.
And he'll be there, and you can all pounce on him at once. Now that Simon has finished his demo, I can tell you all that there is free Wi-Fi available.
Thank you, RSA Web. Yay.
From RSA Web. The access point doesn't have a password, and its name is RSA Web Free Wi-Fi. If you're a speaker, there's also a speaker's room if you need somewhere quiet to sit down and to prepare your slides. Otherwise everyone enjoy tea.